My name is Igor Bray. I'm Professor of Physics and Head of Department of Physics and Astronomy at Curtain Umiversity. You see, we have quite a large group. The senior colleagues with me are Dmitry Fursa and Alicia Kadyrov, and our postdoc is Liam Scarlett. Also, we have Ilham Abdurrahmanov, who used to be a postdoc with us, but now works for the Pawsey Supercomputer Center, and Maciej Satowski is also a senior member of the Pawsey Supercomputer Center. And you can see straight from the outset that we have this tight relationship between our physicists at Curtin Umiversity and the Pawsey Supercomputer Center. And without their support, we could not get our work done. Computers are provided by the Pawsey Supercomputer Computing Center, the Texas Advanced Computing Center, and of course, NCI and funding from the Australian government. Let me tell you about what it is that we do. We calculate collisions on the atomic scale. These collisions go all around us. I give you an example here. You can see an example of positrons scattering on atomic hydrogen here, and all sorts of collisions are possible. This is an example of a rearrangement collision where a positron and electron collide. And our job is to calculate the probabilities of all of these possible outcomes. Just so happens that they're quite difficult to calculate. They're governed by the laws of quantum mechanics, so we calculate probabilities. And of course, probabilities are a bit tricky to find if you have infinite number of possibilities. And that's what happens with atoms and molecules. And charged particles interact out to very large distances. There can be problems, can be multi-centered. And so there's a lot of problems to be solved there, but they have been solved by this method I'll be talking to you about today, called the Convergent Close-Coupling method. And its unique strength is it balances all energies and for all collision processes. Have over 500 publications with over 200 co-authors, 15,000 plus citations, and now over 20 million in funding. Why do we do this? Well, the primary motivation is to provide accurate collision data for science and industry. I'll just give you a very brief overview of all of the range of applications of our work. This talk is not about that, but just to motivate what it is that we do. So the biggest scientific project on the planet is ITER. This is currently being built in Cadarache in France. You can see the scale by the size of the person in the bottom left-hand corner. This is huge. It's about 3/4 of the way built. And its goal is to create abundant clean energy for humanity, which is seawater as fuel. And we provide collisions that go on inside the data for the collisions that happen inside this machine. Also, currently working with CERN on creating neutral antimatter. The example I showed of positron scattering, that's what's required to calculate these particular processes. And they want to understand matter-antimatter asymmetry and how antimatter behaves under gravity. And we will provide calculations to how to maximize the creation of antihydrogen formation. Work extensively with astrophysicists because all light that we see is due to or affected by the collisions that go out in space. And from those collisions, we work out what the ingredients of the universe are. Also, the lighting industry. Lighting fluorescent lamps is just electron scattering on mercury, and the Convergent Close-Coupling method is the best theory for understanding quantitatively those collisions. Even nanolithography, the chips that we all use are made using machines like these, which the nanolithography, the light, it comes from electron collisions on highly charged tin ions. Even medical imaging, PET scans, positron emission tomography. We use positrons for detecting cancer and need to understand how positrons interact with a biological matter. And even medical therapy. There's a new therapy called targeted proton therapy that can deliver the destructive energy of the protons directly to the tumor without any side effects of harming healthy cells. So hopefully that gives you some idea and motivation why it is that we do what we do. Now into a bit of detail as to what it is that we do. In this method, we calculate what's called a transition amplitude. So this quantity here on the left-hand side, that says projectile of initial momentum Ki incident on a target state with initial state transitions to some final state and with a final projectile. This is what we need to calculate, but it occurs on both the left-hand side and on the right-hand side. So we'll write this as T equals to V plus sum. Here's that sum, and V and G and T form linear equations. Here we go. Up here, there's the matrix A. Here's our unknown, and here's what's known. And we'll solve these equations, increase the number of n until convergence. So close coupling comes from the fact that states that you might be interested in a particular amplitude is coupled to all of the other states, so they're closely coupled. And convergent is about increasing this capital N until you get convergence in the system. So the collision system determines the V. So we choose the collision system, and we have two things that we need to do. We need to calculate this four-dimensional array V and solve the linear equations. So some history. In the early 1990s, we had just a single CPU. I paid $60,000 for 512 meg of RAM in the early 1990s, and it was money well spent at the time, but puts things in a bit of a context. We used ALIP, LAPACK for linear equation solve, and the matrix size was about 10,000 by 10,000. By mid-1990s, we had a symmetric multiprocessing architecture with OpenMP. Didn't have to rewrite the code, just put a few OpenMP directives in, and we had a lot more RAM, of course, and we could increase the size of the calculations. Next generation of parallelization was early 2010s, and we implemented MPI to split the matrix across loosely connected fat nodes. And that's the architecture we use to date. Now, at that time, predecessor to PAWSI was IVEC, and this is where we really engaged with IVEC or the staff at IVEC, because we found that their expertise was absolutely critical in guiding us how to take an existing code and to split it up across codes. And we started that partnership more than 10 years ago, and it still continues to this day. So now we use scalar-pack across all nodes. Matrix sizes, can be as big as 500,000 or 500,000 and increasing. And the big functionality that this enabled is the usage of molecular targets. So presently, we're implementing GPU acceleration. And we've applied to the calculation of just the V matrix. Much has been done, a lot more to be done. We are hoping to even solve the linear equation using Slate, but this is not yet ready. How do we go about this? Well, first of all, we need to profile the code, and we use ARM Forge to profile the code. It's very important to emphasize this needs to be done in production mode. So you know exactly where the time goes in production mode, because this can readily change in small test runs. The way we organize the usage of multiple GPUs on each node is that we assign one GPU per MPI process. So we use a hybrid combination of OpenMP, MPI, and GPUs. So we initially use OpenMP to assemble the ingredients for transfer to the GPU. So we know that there's a huge overhead in data transfer to the GPU. So we use OpenMP to generate very large arrays, get them across to the GPU, and do all of the associated multiplications, additions, dot products, all the processing inside the GPU. We've been using OpenACC directives, though through my colleague Igor Bray finds that sometimes occasionally going to CUDA gives certainly to him greater functionality and control, and that can lead to improved efficiencies. Also, he's found that the NVIDIA Nsight Compute Kernel Profiler is very, very useful. It's been a bit of a worry for me to be using GPUs as black boxes, because we didn't know whether we use them efficiently or not, but with this kind of profiler, now we do. And again, the PAWSI staff are absolutely critically important in progressing this. How well has this worked? Well, using Gadi, which has many nodes with GPUs, comparing here their nodes which have Cascade Lake CPUs and the others that have 4 NVIDIA V100 GPUs per node. And the way this is organized, I multiply the number of nodes by the wall time. So perfect scaling would mean that you should have a perfectly horizontal line. So with the red dots, hopefully everyone can see, we've got performance of just under 1200 nodes seconds, and the scaling is very good, but you can see the V matrix takes a very long time to calculate. If we turn on the GPU nodes, and now you get the blue dots over here, so they run, the calculation of the V matrix is around 10 times faster. And so much so that now scalar pack, which is the red and the blues, takes longer to calculate. When you do have these partnerships of high performance computing staff and scientists, then that really enables fantastic new science to be done. And we even publish together. You can see in this particular publication from a couple of years ago, Marcio Sitowski from the Porsche Supercomputer Center has been a co-author on our work, and both Ilcom and Marcio will be co-authors on a lot of the science that has been enabled by the GPU acceleration. Also, the CCC code is available to all via this Amos gateway. This is a group of colleagues centered at Washington, DC, at NIST there. So both the CPU and the GPU codes are available for anybody who's interested to have a go.